So we've got these equations here, and this unit is about systems and solving systems. And so it's basically two equations that are combined together to make a system, right? It's not two equations that are separate. It's a system. They work together, okay? So if you had one equation, a solution to that equation is any point that makes the equation work, right? Any combination of x and y that makes the equation work, okay? And there are a lot of combinations of x and y that you could plug into this equation that would make this work, right? And every one of those combinations makes a line, right? So this line represents all of the different dots that you could plug in to make that equation work. And the other line obviously represents all the solutions for this. But there's only one combination of x and y that would work in both of these equations, right? And on the graph, that spot, that combination, that xy is the intersection, right? That's the only dot that lands on both lines. It's the only dot that would work in both equations. That's what makes it the solution, okay? So when we're talking about solving equations, you're given, or solving systems, you're given two equations like that. You have options for how you solve them. You can solve them using substitution, elimination, or graphing, okay? If you're looking at the graph, you're trying to identify where they intersect. That part is the solution, right? So really, the answer is just the ordered pair. It's kind of hard to see because of this weird shadow that they decided to put in there, but it's 3, 2. I did not make these notes. I would not have done that. 3, 2. And if we weren't sure about that, we could always consult the table as well, okay? So you look at the table, and you're looking, they have the same x column, right? But they have different y columns because they're different lines. And so the blue column is for the blue line, and this red column is that's more of an orange line. So you're looking for where do they share the y value, right? And it's here. 3, 2. Okay. So you can tell by the table what point they share, and that's the solution to this system, okay? It's the only dot that lands on both lines. Right there, 3, 2, and we see that in the table, 3, 2, okay? So that's for lines that intersect. Now let's look at these two equations, and what's peculiar about these two equations in this system? They're parallel. How do you know they're parallel?
Same slope.
Yeah, they have the same slope. Remember this number right here, when they're written in this form, right, y equals mx plus b, slope-intercept form, that fraction, that negative 4/3 part, that's the slope. And so when they have the same slope, like Aiden said, they're parallel, okay? And we see that's affirmed in the picture. These really do look like parallel lines, and so that's true. Now, do parallel lines ever intersect? No, they're never going to cross each other. There's never going to be a point that lands on both lines. And so we would say, although they're both functions and they're both graphs, this is no solution. No solution. Because they are parallel lines. Parallel lines leads to no solution. Okay. And you can see that in the table as well. You scroll down to the table here, and there's nowhere in this table where the y values are the same, right? All the way through the table, and if you kept scrolling in your calculator, you'd never find a spot where they share the same y value because they never actually cross, okay? So the last possibility is an equation that has the same line. And sometimes it's really obvious, right? We look at these equations, and they're identical. It's obvious that they are going to be the same line, all right? But it's not always going to be obvious. Like I could give you the equation 2y equals 6x minus 2, right? And that's the same equation as these other two. It's just every term has been doubled, okay? But it would still produce the same line, all right? So if we look at these that have the same line, where do they intersect? Remember, because the solution is the dot that lands on both lines. So where do they intersect? Yeah, close. I know what you're saying. Literally, all of these dots are solutions, are potential solutions. all of these dots satisfy this idea of landing on both lines, or of working in both equations, okay? So we wouldn't say that it's all real numbers per se, because all real numbers, or infinity, that would be implying that that's a solution, or that this is a solution, right? And obviously those are not solutions, so there is some limit here. But we can say that there is no end, there's no limit to the number of solutions you could have, because these lines keep going forever and ever. And so the potential number of solutions goes on forever and ever as the lines go on. So we say there are infinitely many solutions. Infinitely many solutions. Okay. And we see that in the table as well, right? All of the y values are shared. They're going to share all of the y values. They're going to have identical tables. Okay. Infinitely many solutions. So there are some ways that we can spot no solution and infinitely many solutions when we're solving algebraically. We'll get to those later. But for now, that's what you're looking for in the equations and in the graphs. Okay? All right. So if we want to solve this linear equation by graphing, we just have to graph both lines. So go ahead and graph both of those lines on your own. So hopefully by now you're pretty good at graphing. So this is in slope-intercept form, and the intercept is the y-intercept, right? So this first graph, I'll do it in blue. We're at -1, and the slope is 1, right there, 1 before the x, so the slope literally is 1 over 1. So it's up 1 to the right 1. There we go. So there's my blue line, and I'll do the other in a different color here, red. So that one's y-intercept is positive 3, and the slope is -1. So -1 over 1, down and to the right. Down and to the right. And we can already tell. We can already tell where their intersection is, right here. Right? So the intersection where they cross is 2, 1. Okay? Just solve by graphing. Just graph it, see where they intersect. Great. There's a way in your calculator as well that will, if it's a decimal, like if your intersection is going to be a decimal, I can show you in your calculator how your calculator will find that exact decimal. It's in the calculate screen, calculate section of your TI-83 or TI-84. But yeah, let's solve this system by graphing. If we're given a system that is not in graphing form, what are we going to have to do with these equations? Solve for what? Yeah, slope-intercept form. Is that what you're thinking? Yeah. You want to get it in slope-intercept form, solving for y, getting y alone. So we'd have to do a little bit of algebra there. 2y equals 4. I don't really enjoy dividing negative numbers away, so I'm going to add 2y instead. So x equals 4 plus 2y. Subtract 4. X minus 4 equals 2y. And then I get to divide by a positive 2. So y equals x over 2, that's 1/2 x. 4 over 2, that's -2. And then this other one's pretty easy. Subtract 3x, so y equals -3x plus 5. 5 minus 3x, -3x plus 5. So when we graph those, that's 5. And 3, that's down 3, because it's negative, down 3 to the right 1. and then negative 2, the slope of 1/2, so there are my two lines. And they intersect right there at 2, negative 1. So that's solved by graphing. I know I'm going a little quick, but I feel like you guys are pretty good at graphing lines, so yeah. Okay. We also have a method of solving called solve by substitution. And the idea here is that we're going to substitute nearly one entire equation into the other. Okay. So to get started with substitution, because half the battle is just knowing where to start, you want to get a variable alone. Okay? Isolate one variable. You have 4 to choose from. Choose the easiest one. Okay? Typically, the easiest one is going to be the one that has the smallest number next to it. So of these 4, I'm going to get this x alone because it's got just a positive 1 right there next to it. So x plus 3y equals 5. Subtract 3y. X equals 5 minus 3y. And I'm going to do that so that I can take that and substitute it in for x into the other equation. Okay? If x is the same thing, or it's just as good as 5 minus 3y, then I can put 5 minus 3y in any place that has x, because they are the same. They are equal, as I've shown. Okay. So whenever you substitute for x, the x is gone. Okay? That is the nature of substitution. If there's a substitute teacher here for me, I'm not here, because the sub is here. Okay? So when you're putting this in for x, don't leave the x in there. It's gone. So we have negative 2 times what's replacing the x, 5 minus 3y, and then the rest of that equation, minus 4y equals negative 5. And then you can solve this equation, right? Now this is a one variable equation. We have some combining to do. Distribute this 2, so negative 10 plus 6y minus 4y equals negative 5. Negative 10 plus 2y, right? Combine these like terms. Equals negative 5, and then solve for y. And you should get y equals 5 halves. Did I do that right? Is that what y'all got? So that is substitution. Are we done? We're almost done. What do we do with this y now? Yeah. Now that we know what y is, bring it back over here to x. Bring it back over to where you substituted from. So x equals 5 minus 3, and now we know what y is. So we can plug that in. 5 halves. So x equals 5 minus 15 halves, right? 3 over 1 times 5 over 2. That's 15 over 2. And then 5, well, to subtract fractions, I guess you got to get a common denominator. So 5 is what number over 2? 5 over 1 is how many over 2? 10. 10 over 2 is the same as 5 over 1. Minus 15 over 2. So x equals negative 5 halves. 10 halves minus 15 halves is negative 5 halves.
Can we make it a decimal?
You can, yeah. You can make it a decimal. As long as it's a decimal that ends. Okay. If it's a repeating decimal, let's use the fraction. And I think Math Excel would want that as well. So our answer is negative 5 halves. So we've read it as an ordered pair, 5 halves, which you don't always have to. But if it's x, y, it's pretty common to write it that way because it's an ordered pair. So that is substitution. Get a variable alone and then substitute it into the other equation. All right, and we're gonna jump to our last method, which is elimination. Okay. So with elimination, we're gonna add the variables together. This is another way of solving a system. We're gonna add the equations to eliminate a variable. Okay? And so what we want is the same coefficient, the same number with opposite signs. The same coefficient with opposite signs. So we have just that in this first example. We have 8s, right? If we added these two equations, our positive 8 and our negative 8 on the y, they would cancel out. So we're good to go on this one. Right away we can add it. We can add these equations together. So negative 2x plus 5y, that's 3x. These cancel out. And then equals negative 8 plus 12 is positive, or plus 20 is positive 12. And then we can divide by 3 to solve for x. So x equals 4. And then at this point, I just need to plug 4 back into one of the original equations to solve for the rest of it. So 5x minus 8y equals 20. You can choose the easier one, whatever one you like better. Negatives, I don't really like negatives. So if I can avoid them, I'll do that. So 5 times, we now know that x is 4, minus 8y equals 20. So 20 minus 8y equals 20. Subtract 20, totally fine. You can end up with 0. So it's negative 8y equals 0. Divide by negative 8. Y equals 0. 0 divided by anything is 0. So our final answer here, 4, 0. Okay, so that's elimination. We'll do one more example, and then I need to make some clarifying points. So one more example here of elimination, this one. This one is not ready to eliminate, right? If I added these equations together, neither of these variables would disappear, right? Because I do not have the same number and opposite signs. So does anybody remember how I get same number, opposite signs? If I don't have it. Yeah. We can manipulate these equations to turn them into what we want by multiplying the equation by something. Okay. So you need to decide which variable you want to get rid of. I'm going to get rid of the x because it just looks nicer. Okay. And I'm going to do that by multiplying this top equation by 5, which is totally fine because I'm going to do it to both sides. And the bottom equation by 3. Again, I'm going to do that to both sides. Okay. And that's going to turn my coefficient on the x term. Well, 5 times 3 is 15, so 3 times 5. It's going to turn it into 15. But I want opposite signs. So what small tweak should I make? Yeah, let's make one of them negative. Okay. That way one of them's negative and the x's will disappear when I add them. So we want the same sign but opposite, same number but opposite signs. So I'm going to make that 3 negative. And I did that because it's going to take out that negative, which I think will be really nice. Okay, so when I do that multiplication, I get 15x plus 35y equals 75. And then negative 3 times 5x, negative 15x times 2y, negative 6y, and negative 3 times negative 4 is positive 12. And now I can add these together. Now my x's will cancel out. So they do cancel out. 35 plus negative 6 is 29y. And 75 plus 12 is 87. Divide by 29. And y is equal to 3. 87 divided by 29 is 3. Any questions on how that happened? And then from there, go plug it into one of the original equations. So 3x plus 7y equals 15. I'll plug it in there. 3x plus 7, we now know what y is. It's 3 equals 15. Okay, and 3x plus, so 3 times 7 is 21. Subtract 21. So 3x equals negative 6. Divide by 3. X equals negative 2. Okay. You guys tired or lost or bored? Okay. Hopefully you're not lost. Hopefully just tired and bored. Okay, we're done with examples. I need to make 2 clarifying notes. If it says solve, you can use whatever example you want or whatever method you want. Okay? If you end up with, so if the variables both disappear, then it's either no solution or infinitely many solutions. And you need to know the difference for what you're looking for. In a graph, it's very obvious. The same line is infinitely many solutions. Parallel lines are no solution. But in the equation, when you're solving, it's not that obvious. So if both of your variables disappear and you end up with a true equation, so in elimination, it would be something like 0 equals 0. In substitution, it would be something like 3 equals 3, or 5 equals 5, or negative 7 equals negative 7. Some kind of true equation. Then that is infinitely many solutions. Okay? If both variables disappear, and you end up with an untrue equation. Something like 0 equals 3, or 7 equals 1. Right? Untrue equations with no variables in them. Then that is going to be no solution. So these 2 examples at the end of these notes give you a glimpse of what it looks like when that happens. So if you want to work through those for your own benefit, you can. But you have seen those before, so I'm going to let you get started on your homework at this point. Okay? All right.